Thank you, Martin. So it's a pleasure to talk about this theorem of James Newton and Jack Thorne. So maybe I'll start with just sort of showing you the citation, perhaps which will be recited again when they get the award, so I won't dwell too long on it. So it's made in recognition of the remarkable proof of the existence of symmetric power functoriality for certain automorphic forms, the modular forms, which have already shown up in a couple of talks today, in Anna's talk and in Rahul's talk. So, and somehow they prove a key case of these kind of very important and influential conjectures of Langlands that he made in the 1960s. And somehow Langlands had kind of pointed out this particular case of his conjecture as a key test case, and Newton and Thorne have proven this in their remarkable work. Okay, so here's their theorem. Okay, so what I'm going to try and do is try to explain the statement of this theorem, or rather unpack the meaning in some particular case, and give you some vague idea about the proof. So this theorem has this feature that it's it's the best kind of theorem because you're proving a deep conjecture. The strategy of the proof is very simple and compelling and beautiful. And on the other hand, to really get the strategy to work, it requires immense fighting with great technical difficulties. So it's a kind of dream theorem in some ways. So so I want to in these, as you can see from the slides, I think I have lots of slides. I may not be able to get through all of them, but the subject is vast, right? So that's kind of in keeping with that. So I'll just stop whenever my 20 minutes are up. So okay, so I want to explain the theorem. I'm going to kind of just simplify as much as possible. So I'm going to specialize to a very particular case of this theorem. So I'm going to look at the case of the base field being the rational numbers. And I'm going to look at a particular kind of modular form, right? We've already seen modular forms. I'll briefly say again what they are. I'm going to restrict my attention only to the one particular modular form, right? Because the theorem in this case itself is non-trivial, or it's very difficult. And it kind of gives you a flavor of the statement without really having to go too deep into the theory of automorphic forms. So let me just concentrate on this very particular case of rational numbers and the Ramanujan delta function. All right, so the Ramanujan delta function is kind of a very explicit modular form. It's perhaps the first modular form you typically encounter when you start the study of modular forms, or it's kind of the first interesting one perhaps. And it is given by this explicit Q product expansion. And then we can kind of expand it out, multiply it out, and write it as a Fourier series. And the coefficients, the Fourier coefficients of this series are called the Ramanujan tau function in the honor of Ramanujan. I think this delta function existed before Ramanujan, but somehow he studied it and made these remarkable conjectures about them in his paper in 1916, published when he was in the UK, I think. And so these conjectures have turned out to be very influential. And so let me, in some ways, I can contextualize the work of Newton and Thorne by talking a little bit about this delta function. Okay, so in fact, Ramanujan, I'm not sure thought of it as a modular form, right? For him, it's something, some explicit object, and he stared at it and divined some interesting sort of information out of it. But okay, for us, it is a modular form, and the proof of Newton-Thorne takes place in the context of modular forms. And it's a modular form of weight 12 and level 1, right? Okay, so that's one thing. So we've already seen the definition of modular forms a few times today, but let me just repeat the definition. These are kind of very symmetric functions on the Poincare upper half plane, right? And this upper half plane has sort of these nice symmetries coming by the fractional linear transformations of SL2Z, 2 by T matrices over Z, acting by these Mobius transformations. And they have a certain symmetry property under these transformations, right? So these are modular forms of weight K, level 1, which is the one I'm going to concentrate on today. So as I said, the theorem of Newton and Thorne, of course, is in generality. I'm just giving you this one example. All right. So now these modular forms have a kind of simple symmetry. Z goes to Z plus 1, which then kind of earns them the right of, which gives them a Fourier expansion. And they have this more subtle symmetry, which is this symmetry under Mobius inversion, right? F of minus 1 upon Z goes to Z to the K F of Z. It's a kind of hard symmetry to understand, but okay, it's kind of a very important symmetry. And the group SL2Z is generated by these two symmetries, right? And this delta function, as I said, in some ways is the first example of an interesting modular form you encounter, because it's a modular form of level 1, cusp form rather, of the smallest weight. And it's also the unique cusp form of weight 12 up to scaling. All right, so now in this context, Okay, so now if you look at the 1916 paper of Ramanujan, you find this table, right? He lists the 30 values of tau n for n from 1 to 30, and kind of perhaps just looking at these values and kind of using his intuition, or maybe looking at more, I don't know, but he kind of came up with these conjectures, right? He came up with these influential conjectures about tau n, which can be rephrased in some ways, and in fact, he also rephrased it in, probably this is the form in which he made these conjectures. He said, okay, look at this kind of the Dirichlet series associated to this kind of Q expansion, right? So you look at summation tau n upon n to the s, and then he conjectured, right, that it has this Euler product expansion. So he conjectured that analogously to the Riemann zeta function, which has this kind of product expansion which expresses the fundamental theorem of arithmetic, he conjectured this kind of this sort of Euler product expansion for the delta function, the L series associated to the delta function. Okay, and kind of soon after he proved this, within a year or so, or within a few months, Mordell actually proved this particular conjecture, relying on the interpretation of the delta function rather than a combinatorial cube product expansion kind of thing, by using this interpretation as a modular form. All right, so that conjecture was quickly resolved, and in some ways this is the first time in the history or in the mathematical literature that one has an example of a degree 2 Euler factor, right? In the Riemann zeta function case, which goes back to the Euler's time, one had the Euler product expansion of degree 1. Well, this degree is kind of just by the gotten by replacing that p to the minus s by x, right? So somehow you look at the Euler factor at p of this delta function, and then you factorize it into the product of linear factors and these alpha p's and beta p's, right? So these have some significance. And so I just wanted to point out that somehow Ramanujan's thing was the first example of a higher degree Euler product expansion. And somehow this ties to the fact that delta has something to do with SL2Z. All right. So, and also this kind of this mysterious Mobius transformation or inversion that results in the fact that if you kind of complete this L function arising from the tau function, which is the summation tau n to the s, by tacking on some factors at infinity, by tacking on this gamma function, then it has this kind of beautiful functional equation, right? It transforms this L function, which might a priori be defined only in some right half plane, it kind of gets analytically continued through the entire complex plane. All right. Okay. So now the other conjecture Ramanujan made was that he kind of looked at these values of tau p, where p is a prime, let's say, and he conjectured this kind of rather sort of strange looking estimate 2 to the p to the 2 times p to the 11 by 2, right? Somehow if you replace 11 by 2, which is 5.5, if you replace it by 6, somehow this is very easy to prove, but he conjectured this kind of delicate power saving, which then took 60 years to prove, right? His first conjecture was proven in 1 year. This other conjecture took decades to prove, and then Delin proved this in the perhaps 70s by endowing these numbers tau p, right, which just show up as coefficients, by giving them a higher meaning in terms of Galois theory, right? Somehow he said that somehow they have an interpretation as something more perhaps sophisticated. Okay, so he realized this sort of L-adic Galois representation. Already we've seen L-adic Galois representations in other talks. Some of these tau p's could be interpreted as some of the trace profile of a certain L-adic representation, right? So he gave these meanings, and more explicitly, they appear as the trace of these L-adic representations, which Serre conjectured and Delin proved existed. He interpreted these tau p's as the traces of these L-adic representations as particular marked conjugacy classes of the absolute Galois group of Q, kind of some of the prime sit in there as conjugacy classes, and somehow if you evaluate the trace of this representation at these conjugacy classes, you recover tau p, right? And then somehow this tau p is basically related to the point counting function of some variety over fp, loosely speaking, right? So somehow that was what happened, and that was how Delin deduced Ramanujan's bounds using this interpretation, and of course using the proof of his wave conjectures, right, in the 1970s. All right, so it was a kind of a long story. It took 6 decades to fulfill this, to prove this conjecture of Ramanujan. Okay, and then somehow, just to make this more precise, maybe one can say there's a motive associated to this delta function, and somehow these tau p's are counting the number of fp valued points of this motive, right? Anyway, so I'm going to just make reference to this motive as just some kind of token thing. I'm not going to really explain what this motive is. All right, so now I want to come to the work of Newton and Thorne, right? So now what one can do is you can sort of generate from this degree 2 Euler product expansion of delta, you can generate higher degree L functions. Right, so what you can do is, so somehow you're looking at delta, but then you have this Galois representation, you have this L series, right? And somehow you can try to apply linear algebra constructions to all these gadgets. In one case, the construction becomes the theorem of Newton-Thorne. Okay, but anyway, so let me start with a simpler case. If you can just look at the mth symmetric power of this two-dimensional Galois representation, and then you get the m plus 1 dimensional L-adic Galois representation, right? So just tautologically, you can make this construction. Similarly, you can somehow also kind of amp up the degree 2 Euler product expansion of delta to make a degree m plus 1 Euler product expansion, right? By this formula, you remember that the tau p's were the sum of alpha p plus beta p. They were the eigenvalues of some matrix, they were the roots of some matrix, and you can somehow construct this degree m plus 1, right? Or because it has m plus 1 Euler factors at each prime p. All right, so you can do these simple things. I mean, if you just do them. Okay, and then but now we come to a kind of deep, we come to some puzzle or whatever, something one can try and prove, which is these L functions which one has just defined, are they really, do they have an analytic continuation to the complex plane, just like the L function of the delta thing had, right? So you can ask whether these higher degree, these degree m plus 1 L functions arising from the delta function, do they have an analytic continuation to the complex plane, and with some very nice functional equation where somehow the symmetry is S goes to L m plus 1 minus S. In the case of m equal to 1, which is the case of the delta function, it's 12 minus S, right? So you can ask whether this happens. And now this was predicted to happen, perhaps I don't know, but it's certainly predicted by Langlands as part of a suite of Functoriality conjectures, which I want to somehow tell you something about. I'm watching the time. I don't know exactly when I started, but okay. All right. So somehow these Functoriality conjectures somehow are, it's like a machine which starts from a modular form and constructs more modular forms, right? So in this case, so the kind of the name for these modular forms, they actually somehow traditionally, I mean, you think of them as representations, but okay, but these are certain generalizations of modular forms in higher dimensions, and they are associated to some automorphic functions, so functions with certain symmetries on these higher dimensional versions of the Poincare upper half plane, which already occurred in Anna's talk and maybe also in Rahul's talk. And yeah, these functions have certain symmetries by the SLM plus 1Z, right? By m plus 1 sort of matrices, m plus 1 cross m plus 1 matrices with coefficients in Z. So these are higher dimensional generalizations of classical cusp forms. And in spirit, I mean, somehow the point is that from a cuspidal automorphic form, a representation, you can make an L series, and basically the automorphy property is related to the fact that these L functions have nice properties like analytic continuation, etc. All right, so I'm not really, this is going to be a black box. We're not going to delve too much into the meaning of what this cuspidal automorphic form is, but okay. So now the essence of functoriality, as I kind of already previewed, is that the standard linear algebra operations like symmetric powers on the Galois parameters, at the moment I'm not defining what this Galois parameter is, of an automorphic form sort of predict that some non-trivial non-trivial should be happening with automorphic forms, that you should be getting higher dimensional more and more modular forms starting with one modular form, right? Starting with the delta function, you should be able to generate an infinite series of modular forms associated to each of these symmetric powers, right? And somehow the association will be that the L functions are the same. The L function of this m plus 1 kind of thing object should be the L series of the m symmetric power L function coming from the delta function, right? So somehow that's the sort of spirit of functoriality in this case. Okay, so as I said, this functor, so we are going to look at the m symmetric power of the standard two-dimensional representation, right? You can look at this m symmetric power of this representation, which somehow it just arises from looking at the action of GL2 on the homogeneous polynomials of degree m, right, with GL2 acting in the natural way. And then the symmetric power functoriality is this prediction that this operation should result in a m plus 1 dimensional automorphic form on GL m plus 1 rather, and it should have the right L series, right? If you have that, then somehow it's automatic that you get this functional equation you might want to prove, okay? So more concretely, symmetric power functoriality asserts the existence of a cuspidal automorphic representation, such that the LCDs are the same, or the associated Galois representation, right? Each of these modular forms, the automorphic forms or representations, comes with a Galois parameter, which for us is just going to be a corresponding L-adic representation, right? So the corresponding L-adic representation should indeed be the M symmetric power of the standard of the two-dimensional representation associated to the delta function, right? So that's the kind of conjecture which James and Jack prove in this particular case of the delta function. They actually show that the M symmetric power does actually come from a cuspidal automorphic representation. All right. Okay, so already, actually there's a relation between this M symmetric power functoriality and Ramanujan's conjecture, or Ramanujan's bounds he conjectured that tau p is less than or equal to 2 times p to the 5.5. So in fact, Langlands, I think when he made these conjectures, had already remarked that in fact, if you can prove the functoriality conjecture, if you can show that you have an analytic continuation of all these degree m plus 1 functions arising from the delta function, then you would actually prove Ramanujan's conjecture. Right? So of course, at that time, this was not known how to prove these things, but actually the proof by Deline of the wave conjectures does use this idea of looking at higher symmetric powers, of course in a geometric setting. But so somehow this symmetric power conjecture has been quite important and influential in many developments. All right. Okay, so now that concludes my statement of the theorem, right, giving you some lay of the land. And so let me now give you some flavor of the proof. Of course, the proof is hundreds of pages. I'm going to give you just a glimpse. I encourage you to go and look at their papers. Okay, so the proof of Newton-Thorne is Galois theoretic, right? So somehow though this might look like an analytic statement, one wants to prove some L functions have an analytic continuation. What actually Newton-Thorne work with is the L-adic, are the systems of Galois representations, L-adic, arising from just looking at this M symmetric power, right? So there are some higher dimensions, the M plus 1, GL M plus 1, ZL valued representations. And what you want to show that these representations, they've arisen in a certain way, but actually they are also the L-adic representation of these sort of automorphic forms on GLM plus 1. Right, and somehow you see that somehow there are sort of L-adic representations, one for each prime L. And in fact, what turns out to be the case is it's enough to prove the statement you want is enough to prove it for one prime L, right? And that somehow gives you infinitely many ways or chances or approaches to prove this statement. You can just try one prime at a time, or you might get lucky with one prime. And so somehow that also captures one feature of the proof that you really work with specific primes. Okay, and somehow the proof is kind of amazingly enough an induction on M. Right? So somehow there's actually no connection between sim M and sim M plus 1. So there's in some ways one should not expect to induct on M. But actually it turns out that they use as base cases some known cases of this functoriality for M pretty small, M less than or equal to 4. And then they can leverage that using this association to Galois theory to have an inductive strategy which proves it for all M. Right? So somehow, okay, so somehow, I mean, the fact that they can prove it by induction is of course surprising because there's somehow these M symmetric powers for every M, the corresponding Galois representation is irreducible. There's nothing to kind of induct on in some ways. But what happens is that if you look at the mod L representations arising from these L-adic representations, then they somehow degenerate for small primes L. Right? They become reducible for small primes L. So somehow it exploits this kind of degeneracy of something might happen mod L which is not happening L-adically. All right. So somehow this induction relies on this linear algebra identity, right? That if you look at how the M symmetric power when you reduce it mod L is reducible as long as M is bigger than or equal to L, right? So this exact sort of plethysm order, this linear algebra identity is what I've listed. So if you write M as L plus R, and if you choose your prime L somewhat carefully, that it's not smaller than L, but not smaller than M, but not much smaller than not much smaller than M, then you kind of get that the M symmetric power of the standard two-dimensional representation of GL2 of mod L matrices, right? It breaks up. It kind of reduces. I mean, it has this identity up to semi-simplification. It's a direct sum of symmetric powers, and the key fact is that the things occurring on the right-hand side have symmetric powers for smaller kind of values of that symmetric power, right? So somehow that gives you a foot in the door. Somehow when you look at sim m, it's kind of there's somehow nothing you can do about it. When you reduce it mod L, there's some of this degeneration which happens, and you can now try and induct on knowing having proved the mth power symmetric functoriality maybe for smaller m. All right, so induction, of course, is the strategy of reducing the unknown to the known. So first of all, to be well positioned to do this, right, you kind of have to choose L carefully. So if you want to prove this for the m symmetric power, you choose your L, which exists by the classical theorem of Bertrand, which is maybe from the 18th or 19th century. That there's always a prime between m and 2m, right? So you can choose a prime L so that you can use the earlier linear algebra identity. So by induction, we know that the summands on the right-hand side are automorphic, right? But somehow this is just for a fragment of this L-adic representation you want to prove. This L-adic representation is some huge gadget, huge object. You just know this mod L, right? So somehow, I mean, okay, you've got a foot in the door, but you have to do far more, right? So these congruences give Newton and Thorne a foot in the door to induct on M, and then they can kind of actually do the whole thing by lifting. So somehow you know the mod L stuff is kind of in good shape, but you have to lift this automorphy of the mod L representation, which you might know by induction, to the L-adic representation, right? So somehow there's kind of course, there's this way, and that's of course the technical heart of the proof. Yeah. So okay, I think I skipped a slide. Yeah. Okay. Wait, I didn't. So it is important that you use a well-chosen prime. It has to be small enough so that the mod L representation associated with the symmetric power is reducible, but it should not be too reducible, right? So somehow that, because if it is too degenerate, maybe it's harder and harder to prove these L-adic lifting theorems. So somehow there's some sort of balance you have to achieve. All right. And okay, so what is an automorphy lifting theorem, right? So somehow, I mean, let me just perhaps the second last slide. So what an automorphy lifting theorem is exactly this kind of leveraging, this act of levitation, right? Where you go from mod L to the L-adic thing. So you lift the mod L property of you lift the automorphy of the mod L representation to the entire L-adic representation, which is quite a feat. And this lifting technique was first introduced by Andrew Wiles, I think exactly 3 decades ago, in his proof of Fermat's last theorem. And in an idealized form, right, the automorphy lifting theorem that Newton and Thorne prove is that if the mod L representation arising from these representations we are interested in, which are these m symmetric powers of the L-adic representation associated with delta function, if you reduce it mod L and you know that's modular, and which you know that by these identities I quoted, then you can somehow lift this L-adic property all the way, right, from mod L to L-adic. So somehow that's the summary of the proof in some ways. Of course, I'm not, I mean, there's a lot of hard work and kind of ingenious ideas and overcoming of lots of technical difficulties in doing all this. So let me just say that they prove a close, of course, they prove a close enough approximation to this theorem which is tailored to their needs, and which they call a functorial automorphy lifting theorem. This suffices for their strategy of proving automorphy of the m symmetric powers by induction on M. And the proof of the functorial automorphy lifting is ingenious and requires great bravery in the face of myriad technical difficulties. So I had more slides, but I think I'm going to stop. I think it's, yeah, thank you.